Okay, now we're going to talk about numerical integration. The earlier in chapters of early parts of chapter 5, 5.2, 5.3, we talked about integration by using Riemann sums of rectangles under curves, and those were useful for getting the point across for finding areas under curves, but there's actually some better methods than just that, like the trapezoid rule and Simpsons rule, which I'm going to talk about. And so if you have integrals that are challenging to solve, you can solve them by hand for numerical approximations. And you can even do this if you're with functions that are so abstract that they arise from measurements of data. Like say you've measured a system somewhere, taking timed measurements, and you have all these data points, and you want to find the area underneath that curve, integrate it to see if it matches a model that you've devised. Well, you can actually integrate that using these methods too to find the area under the curve, or should I say, approximate the area under the curve. These two methods I'm going to show you are actually very accurate. They converge on an answer with relatively few steps. And when you are automating this process with a computer in a programming language or a scripting language, for those who prefer like using Mathematica or MATLAB or Octave, you can script them in there, or you can actually write your own program in C or Java, Python to do your approximations. The first of the two methods to talk about is the trapezoidal approximation. You basically draw a trapezoid between two data points on your F curve and find the area of that trapezoid. It has a little bit of hazards. It tends to overestimate when the curve is concave up, and it underestimates when the curve is concave down. But other than that, it gets pretty close. You can see the concave nature of these curves in this graph here. When you have this undershooting that's going on in the first three trapezoids, and then it goes underneath and underestimates in the next four. And so how do you find the area of the trapezoid? It's a geometry problem. It's the width times the average height of those F points. So you take the two adjacent F values on the curve and you average them. You add them and then divide by 2. And that's the average height of your rectangle. You can think of it as a rectangle, and is what the trapezoid is. Just basically take this data point and this data point, add it to and divide to find the average equivalent of the rectangle, which would be somewhere around here. And so that's a fairly accurate method, and it converges pretty fast. And so here's our area of our trapezoid, y0 plus y1 over 2 times the x. That's our function for our area. We can rewrite it as 1/2 times delta x times y0 plus 1/2 delta x times y1 for our first trapezoid. Continue the pattern just simply by replacing y of 0 and y of 1 for each one. Here it's 1 and 2, and then it's 2 and 3, and 3 and 4 for each of your trapezoids. This can be abbreviated quite a bit. The sums of all these trapezoids are shown here, but I separated them into two colors to show how these can be separated out. If you factor out a delta x over 2, you'll get y of 0 and y of 4, the plus 2 times all the other y values in between, which are these. And so, pretty simple model. The part of the trick is finding out exactly which y values do you calculate. Well, that comes from this rule that comes right out of the book. The width of delta x is b minus a divided by the number of trapezoids you want to use to model this. And the first x value substituted into your function is just a. The next one is a plus delta x. Then a plus 2 times delta x. And so on until you finally achieve the end of your list. And yeah, I'll have an example in a few slides here to show this method. I'm going to show it at the same time I show you the example for Simpsons rule. Simpsons rule is another method that was it was originally came up with Johannes Kepler as the Kepler's Faustregel, and that's like the barrel rule is really what it translates to. It's just as iterative as the trapezoid rule, except it actually converges onto the integral much more quickly. It's harder to understand, but it is a faster convergence. In the sense of the rules, the computational time it takes to calculate it is equivalent to a trapezoid rule, but the explanation to proof is a lot more involved. So it was a longer period of time before anybody discovered this. It's almost the same, except instead of a 2 underneath the delta x, you've got a 3. And instead of y of 0 being times 1 and 1 times the last one, as it was before, and 2's in the middle, you end up with an alternating pattern of 4, 2, 4, 2, 4, 2, until finally 2 and then 4. Now with the Simpsons rule, the number n, the number of regions, these partitions you choose must be an even number, or bad things happen. You won't get this 4, 2, 4, 2, 4, 2, 4 pattern to work out. You'll end up with starting with a 4 and ending with a 2, and it will be off. It will be inaccurate. So that the number of regions must be an even number. What this actually does is that instead of modeling the curve with a trapezoid, it actually models it with a quadratic formula, in the sense of ax squared plus bx plus c. And it turns out that by virtue of a fairly long the algebraic proof that they give in the book, that it turns out it can be reduced to this pattern of 4, 2, 4, 2, 4, 2, 4. Pretty amazing at how this works, and it's actually incredibly accurate. Let's look at these error estimates. For the trapezoid rule, as your number of partitions grows, the error is reduced by n squared. You have an n squared in a denominator. So if you have 10 intervals, your error is being divided by 100. If you have 100 partitions, your error is divided by 100 squared. What is that? 10,000. So as your number of partitions grows, the error becomes very, very small, very, very rapidly. Now you have to watch out for this hazard in the numerator. The error is a function of cubed for how wide the interval is that you're integrating across. So as b minus a becomes large, you also have to increase the denominator even more so. So that's a hazard to watch out for. Make sure you have a substantially large number of partitions for a large interval that you're integrating across. But for the Simpsons rule, holy cow, look at this. Yes, you have a fifth power in the exponent here, and yes, as b minus a, as that as your interval of your integration grows, you have a very, very quickly growing error, but you're dividing that error by n to the fourth. So as n becomes large, that's like this denominator is big O of n to the fourth. And that's a pretty fast rate of growth. So likewise, if you have a large number of n, the error is going to shrink very much. And when you compare Simpsons and trapezoid rule next to each other for the same interval where b minus a is equivalent for both cases, the Simpsons rule wins because the error is being reduced by n to the fourth, and trapezoid rule is being reduced by n squared. And we'll see this here. Look for a size of n equals 10. We have an error of 6 times 10 to the negative 3. Over here, 6 times 10 to the negative 6. And over here, oh man, I still screwed up. 624 times 10 to the negative 6. 624 versus 3 times 10 to the negative 6. That's less than 1/200th of the error of the trapezoid rule. 1/200th. It's 200 times more accurate. And look down here, when you increase your n, the number of partitions, to 100 across the same interval, your error goes down even more so. Here it's the 6 times 10 to the negative 6. And over here for the trapezoid rule, it's 400 times 10 to the negative 12. That's 15,000 times as accurate as a trapezoid rule. So yeah, and just the difference is just making 10 to 100 iterations, which is nothing for a computer. You can do this in an Excel spreadsheet, and you would have a very accurate integral just using Excel. It's pretty amazing. It's very, very accurate. So let's take a look at one example here. I chose a fairly simple integral, and it's one that you can solve by hand too if you want. It's not too bad. And it's an integration by substitution. Its integral, I'm doing this in my head, but I can go on and tell you here. Oh no, it's not what I thought it was. It's integration by substitution. You make a u equals x plus 1. You end up with a square root of u dx, and then du is equal to dx in this case. And so that's going to be du over square root of u, and so not too bad of an integral here. You'll have this is u to the negative 1/2, so u is going to be u to the positive 1/2 over 2. Then let me make sure that's right. Over 1/2, which is going to be equal to 2 times u to the 1/2, but we made this substitution x plus 1. So that's what the integral is equal to. I should add plus c. So yeah, it's not too bad. The computational algebra system can certainly solve that one exactly. Most calculators can do that exactly. But we can do this with trapezoid rule as well. And so here in red is our layout of our trapezoid rule as a template. Our delta x in this case is b minus a over n. B minus a, 3 minus 0, divided by 6 partitions, 6 trapezoids, is going to be a delta x of 1/2. So when the delta x is 1/2, 1/2 divided by 2 is equal to 1/4. That's this value right here. Now we have y of 0, and then plus 2 times all the middle ones, y1 through y5, then plus our y6. Now what's our our y value is going to be? Well, we need to find our x values first. And our x values are going to start at 0, and then 1/2, then 2, excuse me, then 1, and then 1.5, then 2, then 2.5, and then finally 3. And so here they are. In fact, I wrote them as fractions, even in places where I didn't have to. I just want to show the point of how they increase. We have this goes from 0 to 3. We start off with 0 over 2, which is 0, all the way up to x6, which is 6 over 2, which is equal to 3. And that's our x terms. You substitute these x's into our function that we had, y over square root of x plus 1, you'll get the square root of 0. Well, if you put 0 in for x, you'll get 1 over square root of 1, which is equal to 1. That's our y0. You substitute in a 1/2, you'll get 1 over square root of 1/2. That's 0.816. There, y2 is our square root of 1 over square root of 2. You might recognize that number from trigonometry. That's the sine of 45 degrees, or sine of pi over 4. And we have then we have 0.632 all the way up until we have x of 6 equals 3, which is going to be 1 over square root of 4, which is going to be 1/2. And so you substitute these y0s into this formula. So this is going to be 1, this is going to be 0.816, 0.707, 0.632, 577, that's going to be 535, and I'm off by 1 here. Yeah, well anyway, yeah, this is 535, and this is 0.500. And substitute these numbers in and calculate it, you'll get that t equals 2.009. Fairly close. Not, it's you got a little bit of error there, but not too much. And then let's take this value over here. This is done with Simpsons rule, n equals 6 partitions. The rule for the delta x is the same as for trapezoid rule. You get it's going to be 1/2. 1/2 divided by 3 is 1/6. That's where our 1/6 here comes from. And times y of 0 for our first one here, and then we'll put in our last one here. Those are the ones that are not multiplied by anything other than 1. And here's our alternating patterns: 4 times y1 plus 2 times y2 plus 4 times y3 plus 2 times y4 plus 4 times y5 plus 2 times y6, and all those products, and then take all that, divide by 6, because it's 1/6, and you'll get 2.000469. And you get this much more precision. Never mind that I did round numbers down for y0 to y6, but in my algebra system that I used, I actually had much more precision, of which I used to calculate this 2.000469. And as you can see, it gets a lot closer to the value of 2. And so that's what goes on with these systems. They work. The Simpsons rule works pretty well. It's pretty amazing what Kepler came up with in this. The Simpson, well, he gets credit for translating it to English, but Kepler was the one who really dreamed this up, but he figured it out in German. Well, I should say that Simpson actually, I believe the story is that Simpson actually discovered this independent of Kepler and published it in English, and it was discovered after the fact that Kepler had actually already done it. And so, because back in the older days, people weren't as well connected in terms of technology as they are today. And so that's these methods. That's how they work. I'll have a homework assignment based on these, but we probably won't do too much in class because these take a very long time to solve. I might do something in Excel, but that'd probably be the extent of it. So take this and have fun with it. I'll see you in class.